Here's one more video that involves proof by contradiction, and this one is somewhat similar to a previous one. We've got a claim that for all positive irrational numbers, x and y, x to the y power is irrational. Now we saw that it's not true that the sum of any two irrationals is irrational. It was easy to come up with an example where the weirdness, the irrationality sort of canceled out. Here, I think it's rather harder to figure out whether that can happen. I think most people's intuition is that raising a number to a power tends to make things more complicated. And so maybe that this actually would be true, that if you raise an irrational to rational, it just gets even weirder and more irrational somehow. Um, so a really good thing to do would be to pause the video and really think about this, and think about what you think of the status of the claim and see if you could prove it or give a counterexample. Um, what we're going to do is a little bit like in the previous case where we found a way to kind of cancel out the irrationality, because in fact this claim is false. But it's a little harder to come up with a counterexample. So I want to show you a very clever way, but maybe a tiny bit unsatisfying way, because it brings up some interesting issues about proof, especially proving an existence statement. So we really want to show. So we're going to actually throw a counterexample to that. Well, we're just going to find. We'd like to find explicit, if possible, x and y that are irrational with x to the y rational. Okay, so first what I'm going to do is I'm going to take square root of 2 to the square root of 2. And again, at any point in this video, if you have an inkling of how to proceed, really pause it and see, because I almost hate to give away this beautiful little trick that's going to happen here. Now root 2 to the root 2, I just picked basically the fundamental irrational number, the simplest thing to prove it's irrational, square root of 2. And I raised it to itself. And I'm not claiming that that's a rational number. And I'll tell you a little bit more about its particular status, okay? But here's the deal. I'd like to show that if it is irrational, I can basically cancel out its irrationality and get back to a rational number. And that's a good thing to think about. How would you do that? How would you take this? So we're actually going to make this x. And we're going to pick a y that makes this simpler. When you raise this to a y power, we want to make it simpler and something that's clearly a rational number. Okay, so, all right, you asked for it. I'm going to give it away. We're going to make y equal to square root of 2. Okay, so let's see what x to the y is. It's root 2 to the root 2, bigger parentheses, to the root 2. Rules of exponents tell us that these multiply. Root 2 times root 2 is 2. Root 2 squared is 2. Okay, so this is definitely rational. It's in Q. Okay. I hope you can see that with the, yeah, I think so. Okay. Actually, let me make sure. I'm trying to figure out how to leave the little webcam preview on, so I'm going to just get a little more room. That's in Q. Okay. So here's what I'm saying. Okay, so this is the interesting part. I never actually verified the status of x, whether it was irrational or rational. There's only two possibilities, though. Okay, so either x was rational to start with, which might be a little surprising. I didn't try to do anything clever, and I think here the intuition is I didn't cancel out anything, and I'm taking a weird number to a weird number. It's probably just really weird. How would this be a rational number? Okay, but we haven't proved one way or another. But if it is rational, I'm done. That's an example of irrational to irrational is rational. Okay, or x is not in Q. X is not rational, in which case, here's our counterexample. That's irrational to the irrational. That's definitely rational. So it's interesting that this doesn't actually show which of the possibilities works. But it shows that there is at least one example. It's just we're not sure which one is the example. That's the part that can be a little unsatisfying. It's not a completely constructive proof. So a constructive proof is where you explicitly create the object you assert exists. And there's a lot of times in mathematics where you can show without a doubt that something exists, but you're just not exactly sure what it is in particular. And that can be a little bit weird. And here is something where we're very close to a constructive proof. It's one of these two, but this proof itself doesn't actually tell us which one. Okay. So I'll tell you, with much more mathematics, some pretty serious mathematics, you can actually show this is actually irrational. So it's actually this case. So this one isn't the example of irrational till irrational is rational. This really is irrational. But then this example does work, totally. Because this is irrational, and this is a rational number. Okay. So this is a kind of a tricky one. Okay. And then in the quizzes. Maybe I'll just mention, I'm going to make this part of a quiz for my students. Find a constructive example. Ooh, I'm not sure if you're going to be able to see that. So here's the goal. Can we get away without this trick? I mean, this is a lovely little proof, really. And all you need to know is the square root of 2 is irrational and this one rule of exponents. It's really quite simple. And you can use logs to find something where you can absolutely be sure, okay, this is definitely rational and this is definitely rational, and when you raise something to this something, you get a rational number. That's not much of a hint. It still might be challenging, but you can think about it.